Good evening, everyone. Thanks for joining us. Welcome to our stargazing lecture for the month of, what is it? It's August already. It's August, almost the end of the summer. I'm Dr. Cameron Hummels. I will be your MC for this evening's event. Thank you for joining us and obeying by the masking rules and the vax status and all of that Caltech requires us to do. This is one of our best turnouts so far post-COVID. So yeah, thanks for joining us. A couple of quick announcements before we get started. These events happen once a month on a Friday night, just like tonight. Our next event, I haven't yet organized who the speaker will be, but I think it's meant to be September 2nd. So stay tuned online on however you found out about this event, Twitter, Facebook, social media, our website, the Caltech calendar, or whatever. We're both having this live. We're also live streaming to a camera over here that's broadcasting on YouTube and such. So hello, online audience. Thanks for joining us. We have a sister series of events called Astronomy on Tap that takes place at a bar in Old Town, Pasadena. It's a little bit less formal because it's not in an educational institution. It's an outdoor patio on a bar. The restaurant is called the Dog House. It's just off of Colorado. So our next one of those will be in 10 days or 10 nights, I guess. It's Monday night, the 15th of August. And the two speakers will be talking about, they're both JPL scientists talking about exoplanets and exomoons. So that should be pretty exciting. Again, like these events, they're free. I mean, obviously, if you buy food or a drink or whatever, you have to pay for that. But what we're doing is free, and we'll have two talks. We'll have astronomy-themed pub trivia with cool prizes. There's live music by musician Jason Achilles, who's a rock musician who plays in between the talks. And then we have telescopes set up there, although the observing there isn't quite as good as the observing that we have here tonight, because it's Old Town Pasadena and there's lights and such. But yeah, I encourage you to check that out. In addition, we started doing some multilingual events, and we will be having an Astronomy on Tap that's only broadcast live. It won't have an in-person contingent, but it'll be entirely in Spanish, and that will take place on Monday, August 22nd. So 2 weeks from this coming Monday. Antonio will be one of our MCs for that event, but I don't speak Spanish, so I can't MC it very well. But we'll have two presenters talking primarily about neutrinos and cosmic rays coming from distant sources in the universe, as well as somebody talking about solar system objects and being able to detect objects in the outer parts of the solar system around Pluto and the rest of the Kuiper Belt. So that should be exciting. I think those are most of my announcements. So the progress of tonight, I'll introduce our speaker in just a moment. He's going to give roughly a 30-minute presentation about the James Webb Space Telescope, of course. And then afterwards, rather than having it go straight to Q&A, what we're going to do is switch very quickly. We have two other scientists that'll join Tony, myself, on a Q&A panel up here and be able to handle questions, not just on the content of what Tony presented on and James Webb, but any kind of physics or astronomy questions that you might have about space science. And because there are four of us who all work on different areas of astrophysics, we can hopefully, give different perspectives and be able to handle a wider variety of different questions that are out there. And at the exact same time as our Q&A panel, we will have the telescope set up on the back field just behind us. If you follow the signs out the front of the door, it'll take you to those telescopes, and you can check that out. So we'll do both of those things until about 10 o'clock. So you can go check out the telescopes and then come back and ask a question, or stick around and ask a question and then go out and see things through the telescopes. The weather looks really good tonight, so I think we'll probably have clear skies for the entirety of the period that we're observing. So don't fret, don't run out to the telescopes worried that you aren't going to be able to see what you're going to be able to see. The moon is first quarter, so we'll have pretty good views of the moon, and in addition see some fainter objects like the Hercules cluster, which is this cool star cluster in the constellation of Hercules, probably the Whirlpool Galaxy, probably the Ring Nebula, probably lots of cool stuff. So yeah, there's plenty of time to see all the things. But yeah, so our speaker for tonight is a graduate student here, Antonio Rodriguez. He is going to be a third-year PhD student here, starting, I guess, right now, next fall. It's the beginning of the school year shortly, so he will soon be a third year. Antonio was raised on the Central Coast of California and did his undergraduate at Stanford University, that you guys probably have heard of, and has been here at Caltech for the last 2 years. He primarily works on optical studies like Hubble and so on and so forth, but using more ground-based instruments like the Keck telescopes in Hawaii or the Palomar telescope south of here nearer to San Diego to look at transient objects. That is short-lived behavior like supernovae and flaring stars and that sort of thing. But tonight he's going to tell us all about the James Webb Telescope, the telescope of the year, I guess, and maybe the next few. But please welcome Antonio Rodriguez.
Thank you all so much. It's so great to see such a big turnout here, and especially so many younger people and sort of people my age. I encourage all the younger people to definitely come up afterwards with questions if you're interested in astronomy, a career in STEM. I'm always happy to talk about it. I'm a little bit closer to that part of the career stage than some of the older scientists. So please don't hesitate and reach out. Thank you, Cameron. Yeah, as Cameron said, I'm a PhD student, which means I'm a student researcher. I don't take classes all day. A PhD student doesn't take classes all day. I also help carry out research and get a perspective of the field in that sense too. I didn't know that when I was growing up, that that's what PhD students did. So just some more input there. Okay, let me start with a question. How many of you have heard of the James Webb Telescope or seen images? Cool. How many of you think they're actually not that interesting? Oh, good. Okay. I was hoping to get out. Good. Thanks. Yeah. I was hoping to get a bigger crowd so I could convince you that they actually kind of are. Okay. If you've taken some introductory physics class, any raise hands? Good. Okay. That's about the percentage that this is aimed for. If you haven't taken one, good. That's perfectly fine too. So let's get into it. You might have seen this image on Twitter or the news, maybe like in the past 2 days or I don't know, past day or so. It was up on Twitter. This is not an image from the James Webb Space Telescope. It's a Spanish sausage called chorizo. They were claiming that that was like the best resolution image of the nearest star to the sun. And it's got some things going for it that as an astronomer, no, really, because so that star is a star known as an M dwarf. And those are actually very red. That's the most common type of star in the galaxy, and they're very red. So as an astronomer seeing this, I might say, oh, you know what, that might be it. The sort of different dots and stuff. If you boil water, right, you'll see like big pots of like big bubbles sort of come up and gurgle up and down and recycle up and down. And you might have heard of the term convection. Our sun's outermost layers are convective. They have the same thing as a boiling pot of water. And these stars, their entire interior is like that. So if you see the different shades, that might think, oh, that's one bubble coming up, that's one bubble going down. I don't know why I'm defending this image. It's not a real science image. Okay, so keep in mind this 2-sentence summary about JWST. It's the world's largest, and it's the newest and largest space-based telescope. So that means it's out in space, it's not on Earth. And the two primary goals, it's going to study exoplanets. Those are planets outside of our solar system, which when I was growing up, my textbooks from the late 90s still kind of weren't sure whether that was a thing. So that's an exciting field for me to always kind of read about, because as a kid, I didn't know whether there were planets outside of ours or not. Its other science goal is that it's going to study the most distant galaxies in our universe. And that's very interesting to know where we came from and where we're going. It uses optical and infrared light. I'll go a little bit into the details of what that means and what other types of light exist. I'm just going to show some images at the beginning. How many of you have seen this image? Cool. What do you notice? Any volunteers? Any people, what's something that struck you from this image? Yes, volunteer right there in the middle. That's exactly the response I wanted. Thank you for pointing out that star. That's exactly the one I wanted you to point out. Yeah, I planted him in the audience. This is stars being born. So this is a star forming region. These are really stellar nurseries. And to form stars, you need gas, dust, and gravity. The darker, the redder colors you're seeing here are actually dust. So you live in California, there's wildfires, and the sky looks a little bit more red because of the dust. That's the same reason that the dust is a little bit darker, a little bit redder in that image right there. How many of you have seen this image from JWST? Okay, fewer people. Okay, that's the planet Jupiter. How about this one? Okay, this is the first image, I think, is probably one of the most famous ones so far to come out of it. And I'm showing you here, I'm just highlighting this little box just to show you the zoom on sort of the resolution. I'm zooming in a little bit to highlight that. Any remarks on this one? Any people notice anything right here in the front? You have the right word. You have the right word. Gravitational lensing. That's the right word, of course. I'll explain what that is in a little bit. But yeah, what you're pointing out is actually those little curved paths that you see there, and it sort of distorts the images. The only way you can really tell that it's being distorted is because you see other objects that have the same sort of colors and same shapes, but they're flat. They're not pulled apart like that one seems to be. So let me answer a couple of these questions. From that, this whole talk is going to be based on that 2-sentence summary. So hopefully you won't forget that. And the question I'm going to answer first is, what is a telescope? Why does this one need to be large? And why does this one need to be in space? And let's begin with just, this is meant to be a talk for really everyone. And to understand what telescopes are, we first should understand what is light. You can already go away from this saying that you know some quantum mechanics, and quantum mechanics says that light is both a particle and a wave. In some senses, you might want to consider it as one, in some as the other. As astronomers, we just want to collect more of it. What you're seeing here is just a fluctuation in electric fields and magnetic fields. You have electricity interact with electricity every day. Magnetism might have a fridge magnet. Those are the things that make up light, and it propagates in one direction. You often say, oh, please turn that light off. It's shining right in my eye. So we have this intuitive sense of light being propagated in one direction. And astronomers, like I said, we just want to collect it because it's coming right at us. And telescopes, all telescopes actually, is a pretty general statement, regardless of what type of light you're looking at. They do two things, and two things only. They're supposed to collect light, and they're supposed to focus it. And the reason that you need to focus it is if you follow those arrows, that's in the sense that you can treat light as sort of particles. They're like particles shooting at the telescope, and you need a big surface for them to bounce off of and then get sort of focused. But by that, I mean you just want to get this big patch of light and narrow it down so that you can study it better. And that's all that the telescopes do. And to collect more light, you just need a bigger area. That's all that matters for a telescope. It's not that it's got more advanced technology or, we're in the information age, right? Everyone wants things to be smaller. Telescopes, you just want to be bigger. You just want more collecting area. These are some components that you need to know. And actually the telescopes that you'll be looking at tonight, they have these components. They have the primary mirror, which is this big mirror that does all of the heavy lifting. That's what collects all of the light. It bounces the light off and onto the secondary mirror, which is in this schematic place somewhere within this tube. And then it focuses into the eyepiece where you'll be able to look at later tonight. And this is James Webb. So the telescope that a lot of you have been seeing on the news previous to this has been the Hubble Space Telescope. And that's what you're seeing on the left right there. That's the primary mirror. Remember, we're talking about the primary mirror being the main important thing for collecting a lot of light in these telescopes. And James Webb is 6 times bigger. So it might not look a lot longer, but the area is the length times the width. So if you're both longer and wider, by being a sort of a circular shape, then you're going to collect 6 times more light. Just to give you a sense of scale, just take a look at the right image. Those are people. Those are some of the engineers that helped help polish and construct James Webb. Okay, so let's get into why it needs to be in space. What I'm showing you here is sort of a schematic of the electromagnetic spectrum. And light is just radiation. It's just these waves or these particles that propagate in space. And these waves or particles, I encourage you to think of them in this picture as waves. And they have different wavelengths. It just how far apart is the sort of the crest from the peak of the waves. That's the wavelength. And going from left to right, that's from short wavelength to long wavelength. And what you're seeing sort of in the text at the top is gamma rays, X-rays, ultraviolet waves. Those are all types of light. And those are all very short wavelengths, short wavelength parts of light. The rainbow is visible light. So when you consider the human eye and what humans can actually perceive as light, it's a very, very narrow window of this electromagnetic spectrum. Moving a little bit to the right, you get into the infrared. I'm going to be using that word a lot. Remember infrared. I might call it IR. And then as you keep going, you get into radio waves. So those are the longest waves, and I'm putting some sort of senses of scale here. Gamma rays and X-rays, those can be the size of an atom. It's really hard to picture a wave having that small a wavelength, the size of an atom. The middle infrared or the mid-infrared is where it starts to become a little bit more tangible. Mid-infrared waves have about the width of a human hair. That's about the wavelength of those. And then once you get out to radio waves, that's almost the size of a football field. You start to get to the 100-meter range. We can't see those from Earth for separate reasons, but those are the senses of scales. I like to think of astrophysics as the science that explores the widest range of scales because we look at all of these types of light. We look at light that comes from very, very concentrated sort of small dimensions, these very large dimensions, and then the universe as a whole. What's really important here actually is that brown part that you see. So the y-axis, the vertical axis there, that tells you the percentage of light that doesn't make it through Earth's atmosphere. So if you see that reach 100%, we can't look at that at all from Earth. And actually, if you look toward the visible part of it, it doesn't go all the way down to 0. So there's some visible light that comes from space that we're not able to see on Earth. That's one big reason to put James Webb in space. We also want James Webb to look at these infrared wavelengths. So as you move to the right from that rainbow, you'll see that a lot of those patches are blocked. That's another reason that James Webb's in space. Also, if you like when it's really windy, you'll see stars twinkle a lot. That's just atmospheric turbulence. The atmosphere is turbulent, just like when you're on a plane and you feel that shaking. The atmosphere does that on very small scales. So it ruins a lot of the telescopes on Earth, or it really limits what they're capable of doing. That's another reason we want James Webb in space. That's the part that James Webb is going to look at. So in this diagram, it looks like it's just to the right of the visible part. And indeed, it covers a little bit of visible light, covers the reddest part. So if we were to see what James Webb sees, it would be just the reddest parts. But the bulk of James Webb, of what it sees, is actually farther redder than that. So the human eye wouldn't be able to see it. It actually looks into what's known as the near infrared and the mid infrared. So there's a big problem that can come about if you want to look at those wavelengths. How many of you have seen like night vision cameras? Cool, you guys have cool lives. That's you're looking at one of those on the left, actually. So if you're just looking at night, this is an image taken at night with one of these night vision cameras, and everything glows. I glow. All of you glow. You're all stars. And what happens is that all of this glowing, all of the sort of electrical parts that you can have on James Webb, all of the other light, everything else that's around it, especially the sun, those can provide a background for the light that James Webb is trying to see. So James Webb needs a shield sort of to keep it cool and to not let all of that other light, all of those other heat sources provide sort of a false background and just drown out some of the light that James Webb can see. Same reason that we want it to be dark when we look up at the night sky. That's why we observe at nighttime and not the daytime in visible light. So James Webb needs a sun shield, and the sun shield that you're seeing, that's the schematic of the telescope on the right. It's that sort of bottom portion. It's made of these 5 layers that can that can keep it really, really, really cool. And without needing any other active sense of cooling, this can bring it all the way down to minus 236 Celsius. The lowest temperature on Earth is minus 90 Celsius. So you need all of these instruments to be really, really cool in James Webb. And you need this sort of silicon that's used for the sun shield that's very reflective, so it can immediately reflect off all of the sun's light without it being able to get into James Webb and provide that sort of background. Who cares about sun shields? They're not that interesting, but it's cool background to sort of know what went into this telescope and all the technology that went in. Really, when people talk about the technological feat that James Webb is, that sun shield it was folded up when it was launched into space, so it had to immediately expand out and sort of fill up that whole volume. And a lot of people thought that was going to fail, and it didn't. So it was really an impressive engineering feat. But I'm not an engineer. I'm an astronomer, so I'm not that interested in that. Let's move on to the images. That's not James Webb, don't worry. That was the best infrared telescope that we had before James Webb. That was the Spitzer Space Telescope run out of the building next door to here, actually. Professor Tom Seufer, I think, was one of the PIs who was very, very involved with Spitzer here at Caltech. And it was shut down right before the pandemic. It had nothing to do with the pandemic, but it was shut down in 2020. And I think the last big event that was held in Caltech for the public was sort of the closing ceremony for Spitzer. And this also looked at these infrared wavelengths. And what you can see here actually is one of the Milky Way's nearest neighbors. Our Milky Way, it's a galaxy. This thing called the Large Magellanic Cloud is known as a satellite galaxy to the Milky Way. It's much smaller, but it also contains a lot of stars, a lot of dust. And maybe here you can see the stars. Can you see the stars up at the upper right? Can you see the gas filaments right there? There's, like I said, remember that image that I showed you of stars forming? You need a lot of gas to form stars. So you can kind of see it. And now that's a much sharper view that we have. So that's James Webb. You can really see the stars that I was trying to point out before. You can really see the gas filaments. So that gives you a sense of sort of how much better the telescope is. If you paid attention and we're looking at the bottom label, at the bottom numbers, they're pretty close. The other one was 8.0. This is 7.7. That's telling you the wavelength that this instrument is looking in. So the progression that I want you to see here is just the size of these telescopes. By aperture, I mean the diameter of these telescopes. These space-based telescopes in 1985, they were 0.15 meters. That's less than a foot. And then now we have all the way up to 6.5 meters, about 18, 19 feet. So it's been a really, really impressive progression that we've seen in these infrared space-based telescopes. And it really is, the name of the game is just a bigger area. That's why we want and need bigger telescopes. So the Hubble Space Telescope is a little bit different than James Webb in the sense that looked more at, it did look at some of the near infrared, but it also looked at visible or optical light and looked a little bit into the ultraviolet. James Webb won't be looking at the ultraviolet at all, actually. So this is an image that we have of a galaxy cluster. These galaxy clusters are some of the largest structures in the universe. And exactly as one of our audience volunteers pointed out before, what you can see at the bottom left, you can see that sort of curvature. And what Einstein said is that if you have enough mass and it's concentrated enough, light coming from behind that mass will then be bent around that sort of mass, that concentrated mass that you see. That's general relativity. The best analogy is a trampoline. If you put something heavy on a trampoline, that'll distort the surface, and light has to follow along the surface, so it'll curve around it. That's exactly why you're seeing that distorted image right there, sort of that curved path. It's pretty clear in this image, right? Welcome, James Webb. So that's the same cluster. That's the same image that you were looking at right before. And here you can see the distortion really, really clearly. Take a look at the bottom left right there. And these clusters are the most massive things that we have in our universe that are so concentrated. Here's just the side to side for you to see one more time. And I'm not cheating. This is actually the same wavelength range approximately that James Webb sees as Hubble in this. I'm not showing you an ultraviolet image of Hubble and a mid-infrared image of JWST. I'm not cheating there. okay, so are these false color images? A lot of people say, yeah, these are photoshopped. And that's what we're going to do outside tonight. You're going to see a lot of cool things. We're just putting up photoshopped images in those telescopes for you tonight. I want you to go away with a good experience. So remember, the human eyes can only see the rainbow part. So if we can't see other parts of the electromagnetic spectrum, we have to assign a color. If we want to look at the images. Because if we just showed you something that's emitting at those wavelengths, you just wouldn't see anything. And this is actually a patch of space that I'm showing you here. And this patch of space I've chosen that near infrared wavelength to show you. You see a lot of stars, looks pretty normal, just like any old patch of space. But when it was first discovered, it was super mysterious. And a lot of pages online say that there's like aliens in this part of space, primarily because this is what that same part of space looks like at optical and visible wavelengths. There's a big cloud right there. And that cloud, all it does is it's a big cloud of dust. So in the same way, remember that I mentioned that dust from wildfires can scatter light and make things appear redder. That's the same thing that we're seeing here, except that it's making it so much more red that human eyes can no longer see it. That's why when you look at those wavelengths, that's actually really blue, at really blue wavelengths. We just can't see it. So while these are false color images that you're seeing online, in the sense that they're not the actual green through red that we see with our human eyes, we have to assign something. We have to assign colors to the wavelengths that we see. So that black line from left to right, that's the range of human vision. And then the ranges that James Webb is going to look at is everything to the right of that. So we just couldn't see anything. So don't worry. It's not a false color image. We're not trying to lie to you. It's just we're providing colors to help you see what all the information contained there actually is, or else you just wouldn't see anything. How many of you seen like this honeycomb, and how many of you have questions about this honeycomb structure? Why does it look like that? Yeah. It's the most efficient packing method, actually. This telescope was so big, it was so wide, that in order to get it into its spaceship and launch it into space, it needed to be packed down. So what you're seeing here is that it's folded, and you need to what's called segment the mirror. And segment just means you need to break it up. And the most efficient packing method is actually through hexagons. If you look at the right, if you try to do everything with little circles, you'd have gaps. And the name of the game in astronomy is to collect as much light as you can. If you have all those gaps, you're just going to lose some of the light. And the reason it's gold plated is because it's highly reflective. We didn't just want to show off our bling to aliens. Great question about the spikes. So a lot of you are seeing these spikes on these JWST images. And the reason that these spikes occur is it's actually two reasons that you're seeing the spikes here. You'll see sort of a main set of spikes and a secondary set of spikes. And it's a combination of just the hexagonal shapes of these mirrors, as well as the support structure. There is a support structure in front of those, in front of that primary mirror for the secondary mirror. Remember that image I showed earlier that it had that little secondary mirror in front? Yeah, so you still need to have that on this telescope. And the combination of those two leads to that pattern you see on the right. And indeed, the first image reproduced exactly that. That's why it was one of the test images. They wanted to verify that everything was working properly and that they understood where these spikes would be coming from. So what's happening with these spikes actually is a thing called diffraction. And it seems a little pesky. It's making these stars that we know to be points look into these sort of spiky things. But diffraction is very, very useful. So I'm letting you in on a secret here, because the public sees images on the news from JWST. Astronomers look at a thing called spectra. How many of you have seen like a CD or a DVD and see that it's like a rainbow if you just look at it? Cool. The younger generation doesn't really see those anymore. Yeah, don't see them anymore. And the reason that you get that is because you have these little gratings, these little chips. That's how you encode music into CDs. That's how you encode videos into DVDs. And the reason that they shine the whole rainbow is because these little slits, these little sort of, they're called gratings, they split light into their constituent wavelengths. So light that we see, just white light from the room, that goes all the way from blue to red. That's why we see that rainbow. And astronomical instruments work in exactly the same way. So this is a schematic. The only parts that you should pay attention to is that you start with white light and you end up with light split into its rainbow. You see it from blue all the way to violet. That's known as a spectrum. Plural is spectra, and that contains a lot of very, very useful physics. And the reason is because spectra are quantum mechanical fingerprints. So one of the basic predictions of quantum mechanics that was verified through looking at stars about 100 years ago, back when quantum mechanics was still thought to be highly speculative and maybe not right. How do we confirm? By looking at stars? Different elements, different things. Hydrogen is an element, helium is an element, carbon, oxygen that we breathe, nitrogen, which is in our atmosphere, they all have these quantum mechanical fingerprints when you look at their spectra. When you split the light, you can see sort of these bands that you see below. The top is a mixture of all of them. So if you see a mixture of all these, if you look at gas that's comprised of all of these different species, you'll be able to decompose it into everything that makes it up. And this is, people always ask me, you're an astronomer, how do you know that's actually going on out there? How do you know it's actually made of this and that? Why aren't you just making it up? It's because quantum mechanics is right. It's because it's right on Earth, and we think that it's right in space. We think it's making the right predictions. We think we understand the physical processes that also lead to the change in these lines, the change in these spectra. So that's how we know what's going on. About 100 years ago, famous astronomer named Cecilia Payne-Gaposchkin, she was the first to sort of say, okay, quantum mechanics, we can apply it to stars. That gave birth to astrophysics. This is how many of you seen this image from JWST? Cool. Okay, good. So it's a smaller portion of people, but I'm going to let you in on a secret. Astronomers are, for the most part, going to look at these types of images, at these spectra. And what you're seeing here, I mentioned that all these different gases have their own signatures. Water has their own signature too. And those are these bumps that you're seeing up there, those bumps in the white dots. So this is looking at planets outside of our solar system. This is looking at exoplanets. And if we look at a spectrum of one of these things, these planets are like Jupiter. They're like Jupiters that we see in around other stars. We see water. So that's how we know the composition of these. You can't get that for the most part if you just look at the images that we show. James Webb's going to do a lot of great, it's going to have a lot of great contributions for exoplanets. Stars are very bright and planets are usually very dim. So JWST has something called a coronagraph on some of his instruments that's able to block the light from the star. And you'll be able to see planets going around it. This is a famous image created by some Caltech scientists too, using ground-based telescopes. And these are the newest science results. I don't think you'll see these on the news. So these I was just scanning through the internet. And these are some interesting new results. I don't know if they're right. I'm not going to say these are right, but these are new speculations based on the newest data from James Webb. The farther a galaxy is, the redder it appears. That's another reason that we want to look into the infrared light. And yeah, that's why JWST is an infrared telescope. These letters that you see here, so the title of this paper is called Schrodinger's Galaxy. Question, is it Z of 17 or Z of 5? If you look at something that has this value, Z of 5, that means it's 12 billion years old. Z of 17 is over 13 billion years old. Our universe is 13 point something, whatever billion years old. So this is really looking at the formation of structure, the formation of things in our universe. And like I said at the beginning, this will tell us where we came from and where we're going. That's one of JWST's big science goals. The oldest stars can also be pro JWST. So in that image that I showed you, scientists have been starting to pull out actual information from it. And what you see there, because of this lensing that I was talking to you about, because of this gravitational lensing, you can see things that are a lot farther away, a lot more clearly, just because they're magnified. And those are those little points right there. It's thought to be a cluster of stars. This was also a paper released this week. They're calling this the sparkler, earliest clusters that we're seeing with JWST. You might look at one of these clusters telescopes later tonight. But these are over 7 billion years old. So those are also in that very, very distant universe regime. And I'm going to leave you with this last image. So this is the newest image. I think this was released 3-ish days ago. This is known as the Cartwheel Galaxy. And I like this because it relates to what I'm studying, actually. So as Cameron mentioned, I study things that change in the universe and things that evolve very quickly. And that's something you should take away too. So we're looking at all these still images, but these still images can tell us a lot about movement. And as astronomers, we want to know about physics. We want to know about movement in space. And the universe is indeed constantly evolving and always active, and galaxies collide. And the image you're seeing right here is the aftermath of one of these collisions, and it's rings of gas that sort of escape outward from this pair of merging galaxies that look like shock waves. Thank you so much. That's my talk.
Excellent. Thank you. Thank you very much, Antonio. We are going, well, we'll take like 5 questions really fast. And then what we'll do is transfer to this full Q&A panel where we'll have 4 astronomers, including Tony, including myself, and 2 other scientists from the department to answer questions. But we also have the telescope set up. I just helped get them set up on the fields just adjacent to here. And so essentially until about 10 o'clock, you can come and go between here and ask a question, go check out views through the telescopes, or vice versa, or whatever. You can do it or just be like, humbug, I'm done with this, and then just walk out and storm back to your car. Whatever you want to do. Like, you're not required to stick around, you're not required to go. But we'll be doing this until 10 o'clock and doing that until 10 o'clock. So you're welcome to stick around for any of it. But first, we'll take some quick Q&A, just a handful of questions for Tony. Questions, sir?
For the galaxy cluster, the Hubble took like 3 weeks for exposure, and then the JWT was like 4 hours. If the JWT took exposure for like a day or 2, would it make any difference with the photos? Would it actually be more information, or it'd be like finite? This is the best photo we could get with the 4 hours.
Yeah, so one of the things actually that that we'll be able to do with JWST, and what you can do with any bigger telescope, is that if you don't need it to look at it for as long as Hubble did, because it's a bigger mirror. You can spend less time looking at the same thing if you want to collect the same amount of data, and you can spend your time looking at other things. So yes, that's a good question. Timescales can be different for the same quality image. Yeah,
But you can get deeper images by staring at something even longer with the larger telescope. So it's not like for most objects, you don't just saturate and then you're like, well, that's all the best image that we're going to get, so we better go on to something else. I mean, you could change to something else, but you could continue looking at it for a longer and get a better, like, more detailed image. You had a question.
How long would the James Webb be able to last for in space? How long would it be able to last?
we promised the public 10 years. Oh yeah, it'll be longer. It'll be longer. So Hubble was very surprising. It's still doing very well. It's been put into what's called safe mode and it's had a couple issues, but Hubble has lasted a very long time. It launched 1995. What is that? Like almost 30 years. 90. Okay. Yes, it's been. Maybe. Yeah, also 10 to 20 years, and it's already outlived that. So yeah, we make these telescopes pretty robust, and we find a way to fix them.
So, for the color of the pictures and stuff, do you assign it based on the elements that are inside those galaxies, or is it based on the redshift, blue shift kind of thing, or what's it based on?
Great question. I'm going to scroll back to that super quickly. So how do we make that like blue, green for whatever coloring and stuff? Yeah, that's kind of a choice. It depends a lot on sort of the manufacturing for those. They're known as filters sometimes, and you can choose filters for your camera too if you have just a camera on Earth. You can indeed just focus around some of the elements. So you can just look at a line of hydrogen, for example, and just focus in on that. And yeah, a lot of images are created that way as well. So it's really a choice whether you want to focus in on something or capture a ton of light at once. Questions?
Hi there. What's the size relation between the Cartwheel Galaxy and our own galaxy?
Question. What's the relationship in the size of the Cartwheel Galaxy versus our own Milky Way? I don't know. Do you know?
I have no idea. Our Milky Way is a pretty common galaxy, though, so I wouldn't be surprised if it's sort of in that range.
We'll figure it out. I'll do some poking around online, and during the Q&A panel, we should be able to answer that question. Other questions? Oh, no, but the people online won't be able to hear you. I'll get shouted out by internet people.
So what's like the main issue that you guys have to worry about with the James Webb in space? Like, something hitting it or something that might cause it to malfunction?
Oh, what's going to cause JWST to malfunction? What are we most worried about? Yeah, it was hit by like some small pebbles, some small things flown out in space, I think like a week ago or 2 weeks ago. That's probably the biggest concern. They didn't do any serious damage to it, though. Some people online said that it did, but it didn't actually. And those are really hard to track. So the really small ones, there's just no way to really track it and to see if there's something that can sort of knock it out. Also, just keeping track of it and making sure that we don't sort of lose control of it for whatever reason. That's happened to some telescopes in the past. There was only one famous telescope that happened to. It's also a worry, I guess, at the back of people's brains, but I think we're pretty okay on that one.
Oh, and to answer your question about the size of the Cartwheel Galaxy, one of our panelists just looked it up. It's about 20% larger than the Milky Way, 30% larger. So it's about 130,000 light years in diameter, whereas the Milky Way is closer to like 100,000 light years in diameter. So, yeah.
One thing you didn't talk about, but that maybe people who are unfamiliar with is why this telescope is where it is, as opposed to where Hubble is.
Good question. It's at a point known as L2. It's called a Lagrangian point 2. So any two things that attract the Earth and the Sun, there's a gravitational attraction between the two, and there are certain parts that are a little bit more stable. This part is really far away from Earth, actually, and also because it's a mid-infrared instrument, we want to get as far away from the Earth as possible, and that's why we have it super far out at L2. It's a lot farther than Hubble was.
Yeah, it can't be repaired. It's farther away than the moon. It's very far. It's very far away. We can take one more question and then we'll switch to our Q&A panel, and then you guys can let loose all of your questions. And you guys online too. We'll get to all of your questions. Sorry, I'm running around too much to be able to handle everything simultaneously. A question from the back.
So for older telescopes, we obviously had like smaller apertures and sizes for the mirrors. How much of that issue it has to do with like being able to get the material, and how much of it is being able to get that actually into space and like functioning properly?
Okay. Challenging question.
If you solve the rocket equation, it's just an equation that determines, if you're taking a rocket, how far you want to go, what its initial velocity, the initial power it has. The more massive it gets, it's not just, if you make it 10 times more massive, then you need 10 times more power to go some distance. It actually scales it's a lot more complicated than that. So you want to keep it as light as possible. And that was a problem back then. Materials were a lot heavier. And just not as well made, and sort of like these sun shields and these mirrors are made from a sort of beryllium mixture. All of that was just a lot more difficult to make earlier. I think that's the main reason why people just didn't make bigger telescopes earlier. I don't know if there's another sort of reason.
Well, one of the things, and I didn't catch all of it, so I don't know if Tony talked about it, but the main constraint on the size of the mirror was what could fit into a rocket as well. And so the James Webb is the first telescope that uses an unfolding kind of procedure to make a small thing that can fit inside of a rocket then unfold in space to be larger than you could fit inside of the rockets that we have available. So that was definitely a constraint on previous generations of telescopes, is what you could fit inside the rocket to send up into space. Okay, as promised, We are going to set up the Q&A panel. It'll take about 5 minutes or so. You're free to stick around and hold on to your questions, or you can go out to the telescopes, which is about like 100-meter walk onto, a 60-second walk onto the field, and view through that, and then come back in here, or vice versa, or whatever. But if you stick around here, you're independent people. You have agency. You can walk around and leave and come back as you please. So we're going to get started with that. We'll have that. The telescopes are set up. And thanks for joining us. I encourage you to come to our next one next month. And we have astronomy on tap in a week and a half. Stay tuned. Thanks. All right. Thanks for sticking around for those of you who are still here. And thank you, those of you on the internet. I'm not waving it. Oh, well, I could be waving at you guys as well, but I'm waving at the webcam that's directly in front of you that's recording. The rest of the world right there. So now is the portion where we're doing a Q&A panel consisting of our speaker for this evening, Antonio Rodriguez. And what we've already heard from him, so people generally, well, I'll let you do like a, talk about what you actually work on, since you were mostly talking about James Webb. Why don't you give like a 60-second thing about what you actually work on?
Yeah. So how many of you have seen Star Wars? Okay. Yeah, I like run the Death Star. Oh, I got a shirt. Very good. And and you've seen Tatooine has two suns. The sun, our sun is kind of an anomaly in that we only have one sun. Half of all stars that have the mass of the sun come in pairs, and more massive stars, they're more likely to come in pairs or in triple stars. And those have been largely ignored. Just they've been difficult to study and they've been kind of harder to find for various reasons. But I study binary stars.
Hi, my name is Nia T. I'm also a PhD student in astronomy department here. And I am so glad that you mentioned some of the engineering marvels that the James Webb had, because I work in instrumentation and I have my background in engineering, and I do instrumentation for exoplanet direct imaging. So what that means is we try to directly take a picture of planets really, really close to stars. As Tony showed that really interesting like figure with the planets orbiting, there's like 3 planets orbiting. Those are directly imaged, which is not the most common way of figuring out about exoplanets. Usually you can figure out information about them without looking directly at them. It's really hard to do that because it's like trying to take a picture of a firefly next to a lighthouse from a really, really far ship. That's how much light you really have to block from your star to get a picture of a planet really close to it. And so I do hardware and help to design, build, test those instruments. Also, I was really excited that today's talk was about James Webb, because my very first internship, I must have been like 19 years old, was on James Webb. And I got to work on and see the sun shield get practice deployed every day when I'd come in. And it was really cool. I'm happy to talk about that more.
So I'm René Jansen. I'm a postdoc here at Caltech and at JPL. And this is a very unusual panel in that I'm also an instrumentalist. So I work actually on the detectors, not for James Webb, because that's already flying, but for even farther into the infrared. So James Webb stops at wavelengths of 25 microns, and that's where my detector starts working. And we're taking it out all the way to multiple hundreds of microns. And we aim to do that. So where James Webb stops, we pick up with more spectroscopy and trying to study the galaxies which are completely obscured by dust, and where even James Webb will have a hard time. So I'm working on a balloon mission currently, which is the terahertz intensity mapper. And there are the next generation of space telescopes. One of the missions we are hoping to fly is not a bigger, but a cooler telescope.
And so I'm Cameron Hummels. I am a researcher here at Caltech in astronomy who, unlike instrumentation people, I do computational like computer simulations of different objects in that we find in space, mostly centered around galaxies though, like different scales of galaxies, either clusters of galaxies or individual galaxies or groups of galaxies, because it takes a very long time scale for those things to form and to evolve, and we can't witness that by just watching it. These aren't such a short time scale these as the things that Tony looks at, where it changes over the course of a day or a year or something like that. Galaxies like that Cartwheel Galaxy that Tony showed at the end take millions and to billions of years to change appreciably. And so, we haven't been looking as a species at the sky for that long with the kind of instruments that you need to be able to see significant changes with these. And so, so we run computer simulations to try and better understand how they behave and make predictions about the ones that we see and how they're going to go into the future, and understand how our galaxy may have been in the past and how it evolved from the sorts of objects that are being seen now with James Webb in the early universe, how those structures may have formed to become like our own galaxy or other galaxies in the present day. So yeah, I guess I'm the odd person out on the panel as the theorist, but that's okay. I don't mind. So we open it up to you guys, and there've already been a number of really good questions online that I'll try and jump over and peruse through and ask. But for those of you in the audience, do you have burning questions about space that hopefully we can address, or questions related to James Webb, or there's a question in the back? It's better if you guys ask instead of us try and interpret what you.
Thank you. I had a really basic question. How do you accurately measure the wavelength of the light particle?
How do you accurately measure the wavelength of the light that's coming to us from distant objects through, and we observe it through telescopes? Do you guys want to, who wants to talk about spectral calibration, wavelength calibration?
So what we usually start with is, you've seen these beautiful spectra, and you can we have a number of sources that we very accurately know spectral lines of. So for example, certain elements, they radiate at very specific wavelengths. So what we can do is we can take a spectrum, which we first do, we take a spectrometer, so the instrument, we shine the light with very known frequencies or wavelengths on there. And then we take a spectrum of an unknown object, and because we calibrated our line with a known source, we can actually then relate the new spectrum to the known frequencies.
I was going to say also a lot of instruments include filters, which are specifically designed to only let through certain wavelengths, certain wavelength ranges, broadband filters, narrowband filters. So it helps you to know that you're only letting through certain types of light. And we can test those like he said on Earth, and like test it with light sources that we create artificially before we put it out and look at something that we don't know what it's made out of. So.
Okay. More questions? Well, actually, I'm going to jump to a question online, and then I'll jump back to you guys. Somebody, Andrew on the YouTube channel asked, who gets to name galaxies? It's a good question, right? Because I don't know about you, and I can't speak for you guys, but my mom would always say, like, you're an astronomer. What are you going to name a star after me? And I was like, Mom, it doesn't really work like that. I wish it did, Mom. But in terms of, like, for the most part, and you've probably seen this either with the JW results or HST results or various results, when some news item comes out and says, oh, look at this new planet, it's named HD 107325b, and you're like, oh. For the most part, these things are named because there's just so many objects of these types that are identified. They're named in a very systematic way. And people refer to them as their phone numbers because they look a bit like a phone number, but it's very systematic, and it's usually, a series of numbers and letters, because you can't have there's only so many finite words that we have in the English language, or names. It initially started where, obviously the planets in our solar system all have the theme that they're named after Roman deities. And then moons for around different objects are named after particular things, like the moons around Jupiter are named after lovers that Jupiter the god had, or the moons around Uranus, aren't those Shakespearean characters, I think? What's that? Okay. Yeah, so you have these sorts of themes, but that's because there's only like 60 or 70 different moons around Jupiter that we've identified. So you can get away with that sort of thing. But when it comes to stars or galaxies, you have to be much more systematic. Now, there are some that fall through the cracks. Some of the dwarf galaxies that are near to the Milky Way, for the most part, they're named by the constellation in which they sit. So there's like, the Virgo cluster of galaxies, or the Botas dwarf, or something like that, Leo 1 or Leo 2, these sorts of things. but there are a handful that snuck through and got named after the person who is associated with identifying them. Like there's a dwarf galaxy called Willman 1 named after Beth Willman, who's a scientist in Tucson at NOAO, the National Optical Astronomical Observatories. But for the most part, that doesn't usually happen. Usually it gets named by a consortium, and the consortium has identified a systematic way to identify these galaxies. So that's, sorry, that's a long response, but that's basically the, yeah, please.
There's also a sort of a reason to not do it because it would create a lot more confusion. But there are, so fairly recently to celebrate the discovery of the first exoplanets, I think, there was the International Astronomy Union gave every country a number of planets to name as they desired. So that happened a few years ago. And what I recently understood is that the field of comets or planetary or solar system bodies, there it is still the habit that the discoverer is allowed to name the object. But that is a very small field, small and specific field in astronomy. So, and there are indeed that many new objects found.
I'm not like a scientist, I think, by training, so I don't usually know all of these famous numbers by heart, like HR 8799. That's the only one I know because it's the only one that people in my field look at, but a lot over and over and again. But I know that you mentioned that there's this database of small bodies, and actually, I think it's maintained, at least one of them, by JPL. There's the small body database, and you can look it up online. And there's a number of them, I think, that they reserve to give out, because when I was younger, like there was a science competition, and one of the awards was to get one of these small bodies named after you. And so they find lots of these like small bodies in space, catalog them, and it you know, it tells you like when it was first found, who found it, but it's just sitting there with no proper name for years, and then they can use them as right. And so you can look into that. I think that there's opportunities to get awarded those, or I don't know if you can buy one, but you know.
Yeah, that's true. So that is, when she says small bodies, she means objects like asteroids or comets or things in the solar system, as opposed to stars or galaxies. Stars and galaxies, I don't think yet have been auctioned off at that level. It's not auctioned off because it's not to the highest bidder. It's certainly to people who've like made a substantial contribution. There are, you know, I think that famous people get them named after, famous scientists, not famous scientists get them named after, and so on and so forth. But yes.
I was just going to add that also some items retain names from earlier times when there weren't as many things known, and they got cataloged. So like the first image of a black hole that we saw that was at the center of the M87 galaxy, which was the 87th object cataloged by Messier, which is what the M is. And then, so then that, as far as I know, doesn't have any other name, but then M31 is what is known as the Andromeda galaxy, but it was originally just known as M31. So there's, you know, there's different catalogs that those names have stuck, and some of those are just letters and numbers, but they've lasted for 150 years or whatever.
That's definitely true. And as was pointed out here and also by Runner, multiple objects will have multiple names depending on, like, in the NGC catalog, it has this name. In the Messier catalog, it has this name. It's known as the Andromeda galaxy, and so on and so forth. So it can be confusing. So that's why people stick to these like phone numbers for the most part, because they're unique. Okay, another question. Don't worry, we'll get to everybody, I promise.
Hi there. Just to preface this question, I work at JPL, so I love space and stars. But a lot of people always ask me, what's the point of JWST and looking out into the sky and when there are problems on Earth? So I just want to hear what you all thought about that.
A common question that I get from people asking us to justify why we should be doing what we're doing. You want to jump in, Tony?
Yeah, there's no reason. We're just, no, I mean, we're saying, you know, here's the spectra, here's the physics, here's whatever. We could be wrong. Like, I don't know. Like we think we're right. You know, we're not benefiting anyone. It's true at all. You should invest in other, well, Yeah, yeah, I gotta take away. Basic science has a lot of long-term implications that someone has to invest in, and you can't predict them from the start. Um, I don't mean to sound preachy when I say this, but quantum mechanics saves people's lives nowadays, and understanding radiation therapy and understanding all of that, that's all really crucial. And 100 years ago, I'm not joking when I'm saying that quantum mechanics was thought to be wrong. And it was really through studying the spectra of stars and confirming it there that we can really verify that that's the right physics. And that's the right physics that governs Earth. That's the same physics that governs us in the universe. The other analogy that I like to use is that it's a little bit like we're studying another country, like we're studying the laws of another country. Because what we see out in space, the physical laws that govern things out in space, they could be very different. The fact that Kepler and Brahe saw that gravity works in space like it does on Earth, we take that for granted now, but that was a really big claim back in the day. So there's a lot of prospects for finding really weird physics in space that may one day benefit us on Earth. And we don't even know it yet, exactly how it's going to benefit us, but it will, in the same way that quantum mechanics had huge benefits for us 100 years ago. Who knows, maybe 100 years from now, we're going to be using the sort of magnetic energy that we see at the white dwarfs that I study, or the neutron stars that we study, to power, I don't know, new medicine or new anything on Earth. So it's long-term gain for a small cost of just, paying me a low wage in the meantime right now.
Yeah, I think that's like from a technological perspective, there's also astrophysics is an extreme technology driver. Like astronomers, if you ask them what they want a infinitely big telescope with an infinite spectral resolution, with an infinite amount of ultra-sensitive detectors that can detect the most distant star in a second. And they want it now. So that all those things, they want the best of the best of the best, and they don't want the best now. They want the best 10 years from now. But they want the best 10 years from now. So there's an extreme technological push to develop new things, which then end up in your smartphone. They are enormous technological drivers, which we don't always see what it will benefit society. But I believe at some point one of the technology directors at NASA did a calculation of the return on investment for money put into NASA, what technology output that game. And that was far outpacing any other investment that the US government did, internal return on investment. And my analogy is always the only other technological driver that is similarly to astrophysics is defense. And do we really want to spend dollars there?
Yeah, I just generally agree with what my colleagues have said on the panel, and just further emphasize that it's very difficult to know what direction the science or the work that we do is going to be beneficial in the future, like 100 years from now. And I've talked about this before at past panels, but 150 years ago, if you'd gotten all the billionaires, or I guess at that time they were thousandaires or something, there wasn't as much money, but if you'd gotten all the moguls together and asked them like to invest in the next technology that was going to really change the world, they probably would have said like steam. And everybody would, because railroads were a big thing, right? And invest in steam, and because that was applied physics at the time. But really, the thing that has revolutionized the 20th century was electricity, magnetism, and optics, and that was being tinkered around by this guy James Clerk Maxwell, that a lot of people thought was just kind of a smart guy, but kind of a loony, and he was flailing around with prisms and circuits and magnets, which that wasn't real. Those were seen as toys, right? And yet he put this together into a cohesive theory of electromagnetism, and that was, that's why we have the internet. That's why we have the transistor. That's why we have computers. And can you imagine the world, if everything had invested in steam, would be the steampunk world that we read about in steampunk magazines, which is pretty cool. but probably doesn't have the same capacity for advancement that we have today. So I just think of that example as a good reminder why it's important to do pure research, not just astrophysics, but pure research on a variety of different, like a very broad subset. Some people on chemistry, some people on optics, some people on biology, and seemingly on topics that might sound ridiculous up front, but you never really know where those transformative ideas are going to come and revolutionize our understanding of the world. So that's my short answer to it, to justify why I do what I do, even when it seems silly to predict the trajectories and the behaviors of galaxies on much larger scales than we probably will ever have the capacity, certainly in my lifetime, but many lifetimes, to be able to go there and appreciate that in person. Okay, more questions? In the front.
So you convinced me of the worthiness of astronomy as a goal. I'm curious, what do you guys think, in the opinion of the panel, is the primary limiting factor in the pace of our discovery, astronomically speaking? Is it too few astronomers? Is it too little telescope time? Do we need bigger telescopes? What is the problem?
Excellent question. Who wants to tackle this? The instrumentalists.
Money. So, yeah, it's money. That's basically what it boils down to. One of the reasons that the current, so every 10 years, the astrophysics community in the US, but also there's an equivalent one in Europe, comes together and says, what do we want to achieve in the next 10 years? And the previous one said, we want to build James Webb. This one doesn't recommend a new space telescope. Well, it does, but a small one. A smaller one. And the reason is simply that things have gotten more expensive in the past 10 years, and the NASA budget hasn't grown equivalently. So they said, we want to build a new James Webb, but in 20 years from now instead of 10 years.
I mean, I would have said I totally agree with that. I think the decadal survey, this every 10-year study that sort of dictates the directions, doesn't dictate, but it gives a recommendation to how the government should spend its money and how scientists should sort of put their efforts and what direction to put them into. Exactly as you said, it's been a huge community discussion. And I just wanted to add as a little bit, not totally answering your question, but it was about like why we do what we do and why the pace of progress is so slow. I think it is hard to convince people of the answer to that question. People who aren't in the field, people who don't come out of the way already. You guys are here. You're coming out of your way to learn something about what we do on your Friday night. I mean, a lot of people who don't see that perspective, it's hard. I get asked that question a lot. Like, why should we put money into this field? And I mean, my answer, I always just jokingly brush it off. It's just like, because I'm a huge Star Trek fan. It's just like, I want that to come true. But yeah, I think that's one of the issues. For sure.
I'm going to play to my audience, and if I ask you guys for money, I don't think you're going to give it to me. So what you might give me, those people, more people interested in astronomy, more people, actually young people who want to pursue careers. Don't be afraid. When I was young, I just didn't really know. I think I was just, yeah, whatever, I'll give it a shot. You'd be surprised that, people that actually get into science fields, where they start from, where they come from. We need a lot of different backgrounds out here. That's really important. So don't be afraid. I think, yeah, a big thing is just people, and a lot of different types of people coming into astronomy is really good.
I love that answer because I actually used to go, I grew up in New York and we had this similar thing at the local university. We had Friday night astro nights and there was observing, and I grew up going to them all the time. And it was totally what inspired me. I really didn't think I was going to be doing this with my life. I went to school and I was like, oh, I'm going to do something really fancy and cool. And I'm doing something fancy and cool. I mean, it started out with me like just trying different classes. And then I realized quickly that like, the James Webb Space Telescope was something I grew up hearing about when I was in elementary school. And I was like, oh, this is going to be some big thing. Who knows when it'll be? And my very first internship in college, it was my very first internship. And I was like, I heard that you guys are working on the James Webb. Like, is there any chance I can work on that? And they totally need people. Like Tony said, just enthusiasm landed me so many interesting jobs and projects that I didn't think I was qualified for. That, we need more people. Is all I can say. We need more interest.
Cool.
Antonio kind of mentioned his when you said that for you growing up and reading in your textbooks that exoplanets, we think they exist, we have yet to find proof of them, and then finding proof of them was kind of a cool moment. I'm wondering if the rest of the panel, if you guys have your own kind of moments that are sort of similar. Maybe it is just exoplanets again for you guys, but maybe it's that the Earth is round or something. I don't know.
Question, what do you guys? So like inspiring moments. What do you guys think? Every day.
I think that is in our generation the one of the main things that has radically changed.
I'd also add gravitational wave detection. I mean, 2016? So people have been like LIGO's been operating for has been an idea and has been building up for a long time, and they've just not been getting results for, decades. So I remember when I started graduate school thinking about working with a guy who was doing LIGO, and one of the other professors is like, don't waste your career working on something that hasn't actually ever had a detection. Why don't you stick with electromagnetic waves? We've been looking at those for thousands of years. And I was like, yeah, but I mean, it'd be like being on the ground floor on something that would be pretty amazing. And in the end, I ended up going a different direction, not because of that cynical guy, but yeah, I think that's definitely a result that has been incredibly transformational for the field and for those of us who've been in it before and after.
Another example of why you should continue doing fundamental physics, because you never know what you find. But another transformational field, maybe more in the very far infrared, is the development of ever greater interferometers. So James Webb is a single dish telescope which can amazing images. But in the Atacama Desert, on millimeter waves, we built a telescope which is basically built up out of 70 telescopes spread over 70 kilometers of area. And that can make extremely high resolution images of, in most cases, for example, the dust around a very young star just starting to form planets. Those first images also were like, we've never imagined getting those at that detailed, like a decade ago.
Well, I mentioned before that I'm an engineer by training. I forgot who asked the question. And for me, I just realized that one of these moments for me, it was less about astronomy, and it was more of my freshman year of college. My dad was like, "Hey, let's go to Florida for winter break," and he timed it, of course, exactly during the time we didn't know it was going to be the first successful, but it was the first successful launch and landing of a rocket, a SpaceX rocket. And it was really influential because I was like, this is the start of a new era. And I mean, we didn't talk about these, I'm not here to talk about rocket science, but it really has changed people's confidence that we can send things up. We can really increase the pace of future space missions, CubeSats. All of this stuff was bursting. It was just exploding in at that moment. And that was it was around the same time that the LIGO discovery was released. It was January of that year, and this was December. It was like literally 1 month apart. And I remember that at my school, there was a huge press release. The auditorium was packed. There was a big panel of people who worked on LIGO, some of the original people who were there from the beginning. They were telling the story of how LIGO was first an idea drawn on a napkin at a local cafe, and they're like, that cafe doesn't exist anymore, but here's a picture. It was like that combination of things happening at the same time for me was like, I want to be at the intersection of engineering and science. And I feel like I totally hit the jackpot because I get to do engineering for the pursuit of science. That's what instrumentation is. And I get to do it for exoplanets, which is even better because Star Trek fan once again.
Questions?
Just like you said, I'm very interested in making that connection with
physical science and engineering. What do you think has been like the most challenging portion of making that bridge together?
The most challenging bridge of science and technology.
Yeah, it's a hard question.
If you want me to start out, yeah. It's just I constantly feel like I'm not good at either one. It's like, am I a scientist or am I an engineer? I feel like I'm kind of in both, so I'm not sure if I'm good enough at either one. It's difficult because I mean, I have my office here in the astronomy department and I go to all these astronomy events and I'm not an astronomer. So I'm like over here making noise, like I do instrumentation, guys. I care about engineering, but I'm talking to astronomers. And then when I'm talking to engineers, they look at me like, you're doing science. We don't know what you're doing, you know. So I love it. I love being at the border because I really feel like I've got a unique perspective to offer both fields. But it also, for me personally, maybe that's just my personality, has been difficult to feel like I'm going to be an expert on something that I could talk to other people on. It's two sides of the same coin because I really feel like it's unique. And I also was very dissuaded when I was in college from doing both. People kept telling me like, why are you choosing two things that are very different? Just pick one and be good at it instead of stretching yourself thin and like overcommitting. I got 2 bachelors. It was really hard to finish my degree in still 4 years. So I had a lot of people, you know, trying to tell me just pick one thing, be good at it. But that was one of the difficulties.
Yeah, I think that completely resonates with me. That's to astronomers, you're the engineer, and to the engineers, you're the astronomer. Until you find out that you are in that one project and you can talk to the astronomers and explain the engineers what the astronomers want. And then vice versa, you can tell back to the astronomers what the engineers actually can do. And then you're suddenly in an extremely valuable position. And that it is an extreme value, and it is valued at certain places and it's valued less at others. And also that it's really dependent on the person you're talking to, unfortunately.
Before I get to a question from the audience here, there were a couple questions online from our YouTube audience that were asking previously when we were talking about when there was a question about what is the biggest limiter for the development of astrophysics as a field. And we talked about people, we talked about money, but there have been a few questions related to what about computational resources? You know, is James Webb putting out so much data that we can't analyze it fast enough because we don't have enough people or we don't have enough computational resources? Do we have to rely on artificial intelligence, neural nets, some sort of machine learning algorithms in order to process those data sets because we can't physically look at everything that's coming in? And for James Webb, that's not necessarily true. You know, James Webb has been taking data and releasing it for the last few weeks. And it's, you know, it's spending the bulk of its time either slewing to an object or looking at an object and then taking, you know, light from it as a series of exposures and then beaming that information back to us. That's true, but it's not so much data that we aren't able to process it. There's a lot of hungry astronomers out there, and all of these data are available immediately to the public as well. There's no, previously with many telescopes, space telescopes in particular in the past, there was a proprietary period where, let's say, well, sorry, this is going to be long-winded, but I'm going to explain it anyway. When James Webb doesn't just point over there because it feels like it. It goes to particular targets because different scientists wrote and submitted proposals for, I'm going to try and do this type of science. I think you should choose my science. And the reason is I'll be able to answer this question like, are there aliens, or what's the size of the universe, or what's the farthest galaxy, or whatever your question is. If the James Webb Space Telescope or whatever telescope looks at that thing, looks at that thing, and looks at that thing for, you know, 15 minutes each, something like that. And then there's a panel of astronomers that looks over all the proposed ideas and says, oh, this one looks good. We like this one. This seems feasible. And it looks like they're going to be able to do what they say they're going to do, and they only require, you know, 2 hours of James Webb time. So we're going to do that. And so this gets done. And that's why right now James Webb is pointing at all the various targets, it's because individual scientists said, I can do some really important science if James Webb looks at that or that or that. Now, in the past with other telescopes, there was a proprietary period where if I proposed something and said, look at that and that and that, those data were taken and sent to me first, and nobody else got to look at them. And I had some period of a few months or even a year where I was able to analyze those results, write up a paper, and then submit that paper before those results get released to everyone, because it prevents, it prevents other people from looking at those results and then writing the paper faster than I can write the paper, because I'm the one who put in the time to write the proposal and came up with the idea. James Webb has no proprietary periods. And so when it observes something, that data is immediately available to everyone, not just scientists, but the public as well. So you can go online and see the data as they are being taken as quickly as us scientists are. And you can scoop us too. If you're like, oh, I figured this out, I better submit that. They got us again. So in some ways, there's cost benefit, right? Like, it's really cool that this is available immediately to everyone in the public, but on the other hand, it's kind of a bummer to the people who wrote the proposals. Why did I bring this up? Oh, I brought this up because the computing power necessary, there are individuals who put together their science proposals and they will apply machine learning techniques to those data to be able to eke out some information that may not be visible or easily discernible to the eye over a large data set. But it's more, computing power is increasingly being used for other types of telescopes. Telescopes that are taking large data sets over large portions of the sky repeatedly. So this is in the work that Tony does, and I'll let you talk about this, but generally for larger surveys like the Vera Rubin telescope, which is not yet operational, but will be in 2 years. This is a ground-based telescope in Chile that's being, I don't know all the statistics, but it basically scans the entire sky that's visible from that part of the world like once every 6 days or something ridiculously high. And so it picks up things. But the ZTF, I'll let you talk about it, also produces an enormous amount of data. That's a survey that's based here at Caltech, produces an enormous amount of data. And yes, I don't think individuals can analyze that data at the speed at which it comes in. And so it gets processed in many ways by computational algorithms that look for the good stuff or look for things that are out of the ordinary. But LIGO is the same way. There's an enormous amount of data that comes in from LIGO. And so using different computational techniques. And soon some of these radio telescopes, like the next generation Very Large Array, will be using these machine learning and artificial intelligence techniques to basically process, because there's so much data. Like, what is it with NGVLA? It's supposed to be like terabytes per hour or something like that.
I think for LOFAR, so that's a radio interferometer centered in the Netherlands, the computation power needed to process all that data is about equal as the data rate it is collecting. Which means that if the data or the weather is bad, they sometimes decide to throw out the data and just observe again, because the computational power is the limiting factor. And there are a lot of developments, for example, in that field to make computation quicker. Going to GPUs and parallel processing helps a lot there. The advantage of us astronomers is we don't have to do all the work ourselves, because computers are a thing all of you like very much. So there's a lot of other companies investing and doing a lot of the research for us.
Yeah, the super quick response to all this is, while in my opinion, James Webb is still an old-fashioned telescope, because you tell it what to point at and then it points at it. Meanwhile, all the telescopes on Earth are getting busy with the robots taking over them. So basically all of the major telescopes of this next decade are all robotic and doing these very big surveys. And as Cameron mentioned, the telescope whose data I work with, that's known as the Zwicky Transient Facility, that has been operational for 4 years. In these past 4 years, it's looked at 2 billion stars, and for each star, it's looked at 700 points in time. That's 1.4 trillion points that it's storing. all of this data, if you're interested in computers, please, be interested in computers because astronomy needs you. And that's, astronomy is going to continue to evolve in a lot of different ways, but it can't escape computers. Fortunately, as Cameron is saying, people find patterns, and it's very much, I can do something super quick. Oh, cool. On Zoom. Cool. Oh, yeah, thank you. So basically the simplest thing that all these algorithms can do, and that you can look at the data sets, there's the names to look out for are Zwicky Transient Facility, and there's a big data set named Gaia that I encourage you to look through. That's all public data. Is you can make a plot of quantity A, you can make a plot of quantity B, and if you look at thousands or tens of thousands of things, if you choose your parameters carefully enough, and you don't even have to choose them that carefully, you might see like a line. You can fit a line to that. That's all machine learning is really. And there's like tens of thousands of points that follow some line. You'll see one that kind of lies out there. And then you use telescopes like James Webb. Say, look at that star right there. You've got an awesome paper right there. So there's still a hope to do really great science in the era of computation.
Questions? Yeah.
Pretty sure our speaker said that James Webb is going to tell us where we came from and where we're going. And I wondered if you could expand on that a little bit.
Where we came from and where we're going.
Yeah, there's a lot of mysteries of the early universe that we still don't know, like what the first stars actually were. Something really mysterious is, and the discovery of this was made here at Caltech, there's something called a quasar. And this quasar is a very, very luminous object that we see. And it was first discovered in, I don't know if it was first discovered in radio or optical wavelengths, but you can see it in radio light and in optical light. And it just kind of looked like a star. Quasar stands for quasi-stellar object, but turns out these are super massive black holes. The same as the black hole at the center of the Milky Way. The one that we have is actually pretty weak. It's only like two. It's about 2 million times the mass of the sun. That's a small black hole. A lot of these are like billions, or up to a billion. Like, I don't know the actual number, but it's like 1 billion times the mass of the sun. And they're very, very far away. They're close to the beginning of the universe. And we don't know how these formed. You could think they formed from early hypermassive stars. They formed from a lot of young black holes merging. We don't know where these came from. So all of that also sort of depends on mysterious forces, including something that's playing now in our universe called dark energy, which leads to the accelerated expansion of our universe. Our universe isn't just growing, its growth is accelerating. So all of these things are intertwined to some extent. So this is why, by studying these farthest things in the universe, by studying how it formed, and looking at the sort of trends that we see until today, we can also get a sense of where we're going and sort of what the different energies in our universe are actually. Very hand wavy answer because it's kind of hand wavy science right now. So that's why we need James Webb.
Questions?
You said earlier in the presentation that James Webb is detecting water using the spectrum. Can you explain a little bit more how exactly it does that?
How does water get detected in the spectra of exoplanets? Do you want to do it? You're an exoplanet person. We can all talk about spectral. And yeah, don't feel like you guys have to stay just because we're talking. You're welcome. Like I won't personally be offended if you walk out. Like you've asked some great questions. So feel free to go check out the telescopes or come back or whatever. So who?
So water has, like basically any other atom, it has very specific emission lines. So if we take again a spectrum, yeah, yeah. So if we take water and we can measure the spectrum of water in the infrared, and if we see we take a spectrum of something out in the universe, and we see the same pattern of spectral lines there, we can say at the same frequencies or close to that, we can say, look, those are lines of water. And then based on the brightness of the various lines and their ratios, we can tell, oh, the water is in that state, or there's this much water out there. Yeah, that looks good.
Oh, yeah, I guess I need to use the microphone. Oh, thank you. So my masterpiece here. So on the x-axis, the horizontal axis, that's the wavelength of light, or the color. So you've got like red over here and blue over here. Or if you go even farther past red into the infrared, or over here into the ultraviolet, or so on and so forth. And then the y-axis represents the brightness of light. So if you were to just take sunlight and send it through a prism, you would get a spectrum of light. You would break that white light into its constituent colors, and some of that would lie in the blue, some in the green, yellow, orange. Everybody knows Roy G. Biv, that whole business. But you'll get some areas where you might get a really bright patch of color at a particular wavelength. Let's say in the green or in the yellow, or you might see a dearth of stuff. You might see an absorption feature where you just don't have very much light of that particular color. Those things, these emission lines, as they're called, the bumps that go up where you have more color at that particular wavelength, or absorption lines where you have less color at that particular wave, or less light at that particular wavelength, are oftentimes the markers of different atoms or different molecules. If I wish I had this, there's this classic demonstration that people have of like a neon tube. Everyone's familiar with a neon sign that you'd see on the side of a bar in Old Town Pasadena or something like that, right? So if you take a prism and you break up the light coming from that neon gas that's trapped in that glass tube and is being electrified, it would show a series of emission lines at very specific colors, the brightest of which are red. That's why, like, if it's really neon gas, then it makes a red color. If it's like purplish, then it's like argon. Like, different gases, when they're electrified and emit like that, have very characteristic emission lines associated with that element. And we can look for those emission lines or their absorption lines when they're getting in their way of a brighter background source behind them, and they absorb that stuff, and you'd get characteristic absorption lines. And that's like, it's like the spectral fingerprint of a particular element that tells you if that element is present in the thing. And I believe in that exoplanet detection, I didn't mean to block you guys with my crummy illustration, but I believe in that exoplanet detection where they found water, they found was it an emission line of water, or was it an absorption line of water? It was an emission line of water. So that's kind of how they do it, is they take the spectrum and then they go, oh, look at this bump. That bump is an emission line, and it's a little bit of extra light at a particular wavelength. Or usually, rather than a single emission line, it might be a couple, like a doublet, and both of those have a specific ratio of brightnesses that like keys off that you know that it's water, or that it's carbon dioxide, or that it's neon, or that it's sodium, or whatever. And then you can say very clearly that there is water in the presence of the light that's like, there's the signature of water in the presence of in the light that's coming to us. Is that okay? Yeah.
If you want to see all these different, like how light is different for different light sources, Google CD serial box spectrometer. So if you find one of these elusive things called a CD or DVD and combine it with a serial box, you can actually make your own spectrometer and look at the spectrum of the or the LED lights here, or a LED light, or an old school incandescent light, or even your laptop screen, and you will see that they all look very different because the light source is very different.
Just to relate that back to the James Webb instruments and all the different instruments that when they're designing, when the engineers of the world decide we're going to make a new space telescope and they're designing which instruments they're going to put on the telescope, everyone's competing to get their instrument on the telescope. And so you really want to choose an instrument that's going to be able to do lots of things, not just one very specific niche thing. So a lot of the instruments, I'm not sure if there was a slide describing, I mean, I'm an engineering nerd, so I guess for me, the most incredible part of James Webb was how those instruments were engineered. And for this, in terms of this like image here, maybe there would be one instrument that does like this range, but then you could change the setup for the instrument, so it could do a whole nother range. It could do a whole nother range. So a lot of these instruments were designed to be able to be used in many different configurations. Not only that, they have like redundancies to make sure that if something goes wrong in one, there's a backup in terms of these detectors and cameras. And then there's actually 4 different even instruments on board James Webb that do different types of things. So some of them are specifically for coronagraph imaging, which is like when you block out a star's light to see the planet. Some of them are specifically for spectroscopic imaging of other types of, diffraction, things like this. There's lots of other types of instruments that are all designed. This is a big point of interest. It's to be able to see all these different things so we can pick up very many different types of signatures instead of just water, right? The spectrum that Tony showed was like a pretty small range, but there's lots of different things that we're looking at. So
Great, thank you. Additional questions? You've waited for a while.
Thanks. So this is a question about exoplanet imaging. As I recall, when Hubble tried to look at Pluto, it's not able to resolve very much. And Webb is bigger, and Pluto's far away in the context of the solar system, but not that far away in the context of the galaxy. So the closest exoplanets are like 4 light years away. They're going around a star that's not very bright. They're going to reflect a lot of light. So the question is, short of an incomprehensibly large telescope that's probably technologically impossible, is there any kind of technology that you could imagine, some kind of, I don't even know what it would be, that would enable us to resolve, to get a direct image of an exoplanet that's not just a point of light, but to resolve more than that, maybe even topography or something, or, is there any conceivable way of doing that short of having an incomprehensibly big telescope? And actually, how big would that telescope need to be?
I definitely planted that guy in the audience. That's for sure. I'm so glad you asked. Yeah, that's totally like exactly what my research, my PhD research is about. Direct imaging of exoplanets, just to give you a little bit of a general idea about exoplanet detection. There's a lot of ways of detecting exoplanets that are not directly imaging them. There's ways to see like, okay, if you're observing a star for a really long time and you notice that its brightness dips at regular intervals, maybe there's a planet going in front of it. There's ways to see like, okay, you're observing a star for a really long time and you notice that it's moving a little bit at some regular rate. Maybe there's a planet that's pulling it in certain orbits. Those are all indirect detection techniques. The direct ones, as you mentioned, are really difficult because you have to block out a star's light. And yeah, it's really difficult to get enough light to be able to get resolved images. So the name of the game is contrast. It's how much of your star's light can you block out to still see enough of your planet. And apart from just having a huge detector or a huge telescope, a huge mirror, there are a lot of advancements that have been made in the recent, I would say like 15 years for my specific field in terms of designing a coronagraph, the actual thing that does the starlight blocking interestingly and differently so that you can save a lot more of the light that you get from your planet instead of also blocking some of that out. There's also been huge new advances where you have mirrors that are deformable. So the James Webb, you saw it's this huge segmented mirror, right? It has all these different segments. These days, there's a new field of adaptive optics where it's been employed so far a ton on ground telescopes, observatories around the world, where you include a mirror within your telescope somewhere. that has thousands of tiny little actuators behind it that can poke the mirror and change its shape ever so slightly. And this is really helpful because you can know, okay, well, there's all these things that our light is passing through to get from whatever star, whatever planet you're looking at to your telescope. And if you can control the shape of your mirror in a way that's clever and smart, you can really increase the performance of your telescope just by having a good idea of what shape you want. And I'm talking micron scale adjustments, really, really small. But that's a huge advancement. And that's been really improving, like on orders of magnitude, 2 or 3 orders of magnitude, how much we could actually see, even if we did ground observing, not just sending a telescope into space. So that's already one huge improvement. And a lot of that is like, okay, let's come up with a good strategy for how we come up with the shape of the mirror. And on top of that, it's just designing optics better, not just improving the size of your telescope, but designing the individual elements that make up how you block out a star's light without throwing away your planet's light, for example. Does that answer your question?
Well, I just did the calculate. It's the diffraction limit. So I just did the diffraction limit for a Earth-sized planet at a few parsecs away. That translate, if you want to observe at approximately the same wavelength as Webb, you would need a telescope the size of Earth, roughly speaking.
But we can, using interferometry, we can create telescopes that are that size that don't actually have to physically be that size. So for instance, everyone's familiar with the whole detection and imaging of the black hole at the center of our galaxy, or the black hole that was present in the distant galaxy M87. Oh, well, thank you very much for this wonderful. Everyone has perhaps seen this image, internet viewers. So that was done with the Event Horizon Telescope, a radio telescope that effectively has an aperture that is roughly the size of the Earth. That's not to say that you didn't know that half of the Earth is covered up by a big radio dish, because it's not. It consists of a lot of individual, large-ish dishes that are 30 meters, 20 meters across. They're 50, 100 feet in size, but there's one in the Owens Valley to the north, 4 hours to the north of here. There's one that's near the Very Large Array in Socorro, New Mexico. There's one that's in South Africa. There's one at the South Pole. They're at these various different locations, and essentially what happens is you can collect data at those individual places at the same time, and then combine their signal to pretend like it all came from different parts of an Earth-sized telescope. That's this phenomenon that we describe as interferometry. You're using the interferometric, the interference patterns from the light that's going to these various different sampling places, these individual telescopes, to put them together into a much larger aperture. So you can do the same thing, not just in radio, but you can do it in visible wavelengths with an optical telescope like the Keck telescopes or the Palomar or Mount Wilson. Pick your favorite telescope. You can do this. It's just a lot harder, because when you put those signals together, the time resolution that you have, like each of those observations has to be tagged with a very specific time when it was taken, so that you can combine them together on par with the exact same time that they were taken at these different locations. And the time resolution that you need, or the time precision that you need to have, is proportional to the wavelength of the light that you're using. So for radio waves, which have very long wavelengths of light, centimeters to meters to kilometers in size, you don't need incredible, you already need really high time precision, but you don't need ridiculously high. But for optical wavelengths, it's very, very challenging. And so that means it's hard, and it means there's only a handful of facilities in the world that are able to do this. And usually it's from specific locations where you have optical fibers that combine them in situ, instead of having to process them onto a computer where you've mapped really carefully what the precise time when it was taken. You need atomic clocks to do this sort of thing, and people haven't really figured out. But that is enough with my rambling. The point is that this can be done in the future when our technology is improved, in a decade or 2 decades, to be able to combine these from an Earth-sized aperture. The other thing that some of the people suggested online is using gravitational lensing of another star at a distance to be your telescope, to be your lens, and then you can do that sort of thing. But you have to be at a very specific distance to that gravitational object, like a star or a galaxy, relative to the planet that's directly behind it. So it's very hard to align things in that particular thing, but you would be able to achieve the resolutions that you're asking for, where you can resolve structures on that planet that's around that distant star. It's just harder to align it, really. Okay, enough with my rambling. You guys won't have anything to add on that? Okay, lots more questions. And 6 more minutes. We'll get through stuff. I already answered a question of yours. I already answered a question. We haven't answered a question of yours.
Like robotic systems were mentioned. So I wondered, how do you feel about the prospects of like nanorobotic spacecraft and that type of kind of confirmation methods or things like that, if that makes sense?
Telescope robotic spacecraft? Where, so like a question about it's the robotic telescope is identifying what the sources should be and where it's pointing, as because many telescopes are robotic to some extent. They have motors that control where they're going, but you're talking about like it making its own decisions about what it's going to observe. Okay. I mean, ZTF at some level is, right? And Rubin, right?
Yeah, that's already happening. I mean, you can optimize, you can sort of then learn from your own previous data and look and sort of let the telescope make decisions of where you want to look at next. Well, not the telescope, the computer behind it. Yep.
Oh, sorry.
One of the other main developments is that instead of going bigger, a lot of astrophysics is actually looking into going smaller. So CubeSats are a huge development. And of course, astronomy tries to leverage that. Like we could build a swarm of satellites and build an interferometer, which could easily become as big as we want because we don't have the physical limit of we're limited to the size of the Earth. We can make it as big as and as small as we want. So there's definitely ideas to basically do swarms of small satellites for these kind of purposes.
There was a talk given in January at our Astronomy on Tap that if you go to our YouTube site, you can find where a scientist who used to be a scientist here, his name is Dr. Dmitry Duev. He's a Russian scientist working on the ZTF project that Tony was talking about earlier. He was doing a lot of the design of the machine learning algorithms and describes how the ZTF project works by like basically operating robotically, where it points at this and then it figures out, oh, there's some really good stuff there. Let's follow up on that particular target. It's making the decisions on where it needs to look over the course of the night to find the needle in the haystack of all those data that are present. And it's not obvious in real time. Humans aren't processing that data as quickly as it needs to be in order to figure out what the next targets are. So I encourage you to check that out. The other speaker on that night's event is really good too, because Dr. Amy Meinzer, because she she's this high-profile scientist who also happens to be the technical advisor for the movie Don't Look Up that came out about 6 months ago about the comet. No, it was an interesting movie. A disaster movie, but yeah, she does great science and works specifically on that sort of project. So I encourage you to check it out. Astronomy on Tap from, I think, January of this year, 2022. Mind you, I'll get to you in a second.
Thank you. And thank you for this, by the way. It's been really interesting. So I'm an engineer, and I got to go and tour and see James Webb and Northrop Grumman before it launched. And from the engineering perspective, I was just astounded by it. From, individually actuating mirrors and tensioning system on the solar shield and all that, I thought if it makes it into space, 1,000,000 miles where it's supposed to go, will be amazing. And so I was wondering, from all of your perspectives in like the astrophysics and astronomy world, have there been any like really big, exciting findings that you all can tell or that have been, in the works in the last couple weeks with the data being published yet? Or what are your, interpretations?
Yeah, so Tony mentioned a few of these things at the end of his talk. The only one that I wanted to highlight is there have been a lot of claims of the most distant galaxy ever found from James Webb, primarily from that initial deep field image that was shown during the press release that Joe Biden gave, and then the next day that was better than the one Joe Biden gave. But it's this, I think it was a 12-hour exposure or so of a bunch of galaxies, and so you can see the light from them. And there have been, at my count, there have been 8 papers already written about what the most distant galaxies that are present in that field are. And they talk about them in terms of the redshift at which those objects are. Redshift is kind of a confusing subject, so we don't have any time, so I'm not going to talk about it. But it basically means the farther, it's a proxy for the distance or the age of the galaxy at the point at which that light was emitted. But the crazy part is, so these 8 different papers written by 8 different teams have identified these different galaxies somewhere between redshift of 10 and 20. Previously, the highest redshift, the most distant galaxies that have been identified from Hubble Space Telescope or other instruments are at like redshift of 10-ish, right? 10-ish, 11-ish, something like that. So these are all record breakers, right? But of the 8 different studies, if you plot them up, almost all of them look at that image and find different galaxies as the most distant galaxies. So there's not very much agreement between these 8 different groups, which you'd expect there'd be a little bit more agreement. And it's because they're not using spectra yet. Spectra, we talked about these spectral emission features or absorption features to identify a particular element that's present, and thus also identify how quickly it's moving away from us, which gives us a proxy for distance. They don't yet have those data, which is kind of the gold standard for identifying the distance and the redshifts to these. They're just doing it based on photometry, just based on the images and the colors from those images. So it's not really, take it with a grain of salt is what I would say. But probably in the next 2 months, there'll be spectra and they'll be able to better categorize that. But I think that's a really interesting result. I mean, it's very early on in JWST, so there aren't a ton of results yet. Mostly it's just like cool pictures and stuff, and highlights and headlines like, oh, we discovered water and so on and so forth, which is awesome. But like in terms of results, the highest distance, highest redshift objects are pretty exciting. And I expect that that will continue to be broken over time as more and more data are taken. But I just talked a lot. You guys want to add? You talked all about this.
I don't know if he showed it, but from the image of all these distant galaxies, a few have been taken spectra of. Those are galaxies which now have been spectroscopically confirmed to be 13 billion light years away from us. But still, with very quote unquote short exposures, we have exquisite spectrum showing neon, oxygen, hydrogen. These are spectra that we are used to seeing for very nearby galaxies. So that to me is extremely exciting, because that's the way we can not only uniquely confirm what the redshift are, but also learn a lot about what's going on inside these galaxies. The other thing, you mentioned technology. So the adagium of NASA is don't have any moving parts in your telescope because they're gonna break. Webb had many moving parts, and all of them worked perfectly. I think that's the biggest miracle of Webb.
Yeah, I was gonna add on that engineering note. I was just checking my numbers today, and someone asked like the lifespan of James Webb during Tony's talk, and the estimate was like 5.5 years to 10 originally. But then when it was being sent out, the fuel savings were so good that I remember one of the directors or some high up person posted like, "Oh, we expect James Webb to last at least 20 years. They just doubled the lifespan, just based on how well we were able to launch it." And then on the note of the actuators, there was over 144 actuators in the sun shield alone. So much redundancy, just in case anything went wrong. And then 300 and something actuators overall. This is the first time we've ever sent a telescope out there that deployed in the way it did. And I know that someone made a comment earlier about how we're sending this spacecraft to L2 a million miles away, so much farther than Hubble. It really was so critical to understand that it could not be serviced if something went wrong there was not going to be any chance that we could send anyone out there to fix it like we were able to with Hubble. And so just the engineering, I think, was also really exciting, like you mentioned. But just to reiterate, like how impressive it really was to make sure to be totally, considerate of the fact that everything has to work. And then one other point that I looked up in terms of numbers, in terms of impressive engineering amounts, was that Hubble, I was looking up the weights. Hubble was about 11.1 metric tons. It was super heavy. It was going close by. It was fine. James Webb, think about how much bigger it is in terms of size. It was less than 6.5. So like almost half. Yeah.
Yeah. It's gone. Okay, it's 10 o'clock. I will answer your question because I promised. I'll answer all the questions, but we have to shut off the live stream and I have to let my volunteers go. So I want to thank everybody for sticking around. I want to thank Tony. Excellent presentation. Thank you very much. Mia, Dan, Reiner, thank you guys. Wonderful on the Q&A panel. Thank you, audience online. Thank you, audience here. Our next event will be Astronomy on Tap, not online. Sorry, guys. On Monday, the 15th at the Doghouse. Go to our website to find out more information. Our next stargazing lecture is in a month, and we'll have an Astronomy on Tap in Spanish in 2.5 weeks. Thanks, everybody, for coming. Bye.